So we want some examples that show us all the interesting things there are to see. And that mainly comes in when we have fraction powers of x, our last type of function. Now, to keep it as simple as possible, for the first time you see this, I'm going to look at just one term, and I'm going to look at x to the 1/3. Now, I can write it as x to the 1/3 or cube root of x, of course, and you should see that this is defined everywhere. It's defined for all x. It's not the square root. Cube root's defined everywhere. Cube root of anything you can find. So I don't have any asymptotes. No asymptotes or anything. So out of step 2, really nothing is coming. Not much. Okay, so let us see, what does the derivative tell me? Well, for the derivative, I'm not going to use the root version. I'm going to use this version because I can then directly apply the power rule. So it's going to be 1/3 x to the negative 2/3. Now I don't want to look at this version. I liked it for the power rule and for nothing else. So I want to maybe leave the third in front, then move it so I don't see a negative power of x. And perhaps you like the root version moving forward. Always know that it's an option, like so. And I do like the root version for anything other than derivatives. And I'm done with the derivative now. I had a reason to clean this up because I need to now see, where is this function equal to 0? Where is this function, the derivative, undefined? So there's no benefit right now to make the fraction power of x function complicated. Let's just look, this is in that type. Let's just look at a simple one that we can quickly do. Where is this derivative equal to 0? Is the question for you. Have you learned from the previous example? Or every example is teaching me something, actually a bunch of things. Where is this derivative function equal to 0? For which x values? None. You're saying nothing? It's none. You're right. Never. Again, not 0. But it's good that you're saying this so that you can learn. If we don't say something, even if it's wrong, we're not going to learn. It doesn't stick. By making mistakes, you remember it way better. It's way better. When the only things that can make this fraction 0 is numerator being 0. A denominator equaling 0 will make it undefined. It is important, but it wasn't in the first one, it's in the second one. When x equals 0, the denominator will equal 0, and it will make the whole thing undefined. So, of course, you said that on purpose, just so someone can say something. But please, please understand that when I'm looking at a fraction, which one, the numerator or denominator, which one affects which result? Very important. And it happens all the time. All the time. Don't feel it's just you in any way. That's why I'm making a point of this. That people swap the roles of the numerator and denominator. I can have a denominator. It doesn't matter. The answer will never be 0 until the numerator equals 0. Okay. So out of this, not much is coming, but I have one interesting point. X equal to 0. So I'll just mark that off. So my x values are split in 2. Okay. I have a third floating around, and I won't write the 1, of course, that's doing nothing. My cube root of x squared. So the pieces that I have to work with in the case of fraction powers of x look a little different, often. Not always, often. A third is always going to be positive. This is where I really like the cube root, the root version, which in this case is a cube root. It's going to be 0 when x is 0. Of course, this all combines to make the derivative. Because this piece features in the denominator, it makes the whole thing undefined, in this case the derivative. Which side do I want to do first? Maybe the left side of the interval. I need to fill in pluses and minuses. To the left of 0 for x, I have negative x values. But when I plug it in there, I work inside out. I square, making it positive. Cube root of a positive number is positive. For positive x values, of course, it's going to be positive. So you see here, it's not always going to go negative to positive. Sometimes it's the same, sometimes it's flipped. You need to think about the piece that you are working with. And I see here, 2 positives will make a positive, 2 positives will make a positive. So it looks like nothing is happening. I have an upslope, bad times, upslope. Okay, this example, we don't need the fraction powers of x to be complicated to show us its complications, I'll call it. So now my sentence. Again, my sentence refers to the original, and this time it's called y, is increasing on what? Do I say, do I say this? Sorry, that was an ugly infinity, I apologize. Or do I say this? It's one of them. Which one is it? We have 2 minutes. But don't take 2 minutes to respond. This is our last little bit for today. And then we'll do another example and another one and move on and just take as long as we need to take. We can't skip these things. They're too important. Because I can't trust that you're going to discover all of these little things, and when you encounter that in a problem you're doing on your own, are you going to know what it all means? No, that's my job. That's why I'm here. I agree it's one of them. This is the first or the second. And this is where I need to train myself to remember all conclusions I am making is in regards to the original function. And you see here, even though the derivative is undefined at 0, which clearly it is, the original function is defined everywhere. What is the cube root of 0? It's 0. The original function has no problems. It has no asymptotes, it has no holes, it has nothing. It's perfect. It's actually the y-intercept is at x equal to 0. Let's get a picture of the graph that we would have at the end of step 2. We would have a y-intercept right there at 0. We would know it's going up, we would know it's going down. That's all we know. There's a point. It's all good. And this is a good example to show that just because the derivative is unhappy with an x value doesn't mean the function is unhappy. Function is perfectly happy. Now, this is a first example where I haven't seen something like this before. What on earth is then happening? I have a graph throughout, one piece, nothing strange is happening, yet the derivative is undefined. If I think about straight lines, almost all straight lines have a slope. Almost all straight lines fit y equals mx plus b, except one. Except one straight line does not have a slope. Its slope is undefined. It's the vertical straight line. So if there is a graph here, there's a tangent line, yet there is no slope. The only way that can happen is if I have a vertical tangent line, which is what's happening here. And very often with fraction powers of x, I have a vertical tangent line that needed to curve away a little bit. So this I have not seen before. If I have a function that's defined everywhere, yet the derivative doesn't exist, vertical tangent line. Vertical tangent. And I get these interesting things when I look at the fraction powers of x type of function. But I mean, that's okay. I need to see it in an example, maybe a couple, to get more comfortable with it. The first one's never going to be super comfortable. That's okay. That's okay. It's still always increasing. Compare any 2 points. Compare the y value. Always going up. It's always going up. It's just super steep. As steep as you can imagine for a moment. And then it flattens a little bit again. All increasing. And I'm building that experience slowly by looking at more and more examples. Let's make it a little bit more interesting. Not super interesting. A little bit. And we will see these functions again. Let's look at this guy. X minus 1 all to the power of 2/3. Let me just make it clear what my denominator is. It is a 3. All right. So now I have no idea what this graph looks like. I see a fraction power. Yeah, the fact that it's x minus 1 in the bracket just means there's a little shift happening. It's not really a different type of function. So I am going to find the derivative. And that's going to be a chain rule. It's something to the power of 2/3. So the first part of the chain rule will be 2/3 times the something to the power 1 less, which will be negative 1/3, times, says the chain rule, by the derivative of that inside something, which is 1. Now, for the purposes of moving forward into my table and seeing what is happening with this derivative, I do want to clean this up as much as I can. For me, personal preference is to get rid of the negative exponent. So I will move it to the bottom. And perhaps I want to just remind myself that whenever I need to see it this way, this is just the cube root. Maybe that helps me, but either one of these I like before I move forward. So I have a reason to simplify because it's going to make my life easier for my upcoming table. So I'll do it over here. There are 2 things that I want to check. I want to check when is the derivative equal to 0 and when is the derivative undefined. Always going to be those 2 things, no more, no less. And the more we see them, the easier they will get. So I see that in my numerator, I only have 2/3. There are no x's, and only the numerator can make the function 0. So that's going to be a never. I do see I have something in my denominator. When x is equal to 1, I will get a 0, making the whole thing undefined. All right. So we will list all the numbers we get out of these 2 checks. In this case, there's only 1. And I'm going to list all the pieces that I see. I see a 2/3 and I see a cube root of x minus 1. Together, they combine by way of multiplication and division to give me my derivative function. Now 2/3 is always positive. Not a problem there. But I don't want to miss anything here. If that 2/3 was a negative 2/3, then it plays a bigger role. So I just get into the habit of listing absolutely everything I see in my function. Cube root of x minus 1 is 0 when x is 1, and because it's in the denominator, we've said it makes the derivative undefined. Okay. Now, this looks perhaps a little bit uncomfortable. To the left of 1 is this positive or negative. A shortcut that you can take to make it easier is I can take a representative number inside this interval. It's 0, so it's inside this interval. Plug in that number, but then I get cube root of negative 1, which is negative, and it's going to be negative for all of them, as long as I've listed everything that I got from these checks. And I've split up my table correctly. You can take a representative number, and whatever it does for that piece, the whole section will do the same. So I'll put a representative number of 2, something easy I can easily work with in my head. 2 minus 1 is 1, cube root of 1, positive. So that's one thing you can do if the component that you're looking at is a little bit less familiar. Now, a positive and a negative will always make a negative. 2 positives will always make a positive. So my slope lines are going down, bad things happening, going up. So it's not a little cup that it's making in the conventional sense, because I do not have, I'll emphasize it here, there's no horizontal tangent line here. That would be when the derivative is 0, and that's not the case here. So I do go from downhill to uphill, but let's see what's happening here. Let me set up a graph so I can at least visualize something. So, of course, we're just doing step 3. And again, that is not sufficient to clearly know what the graph looks like. If I did step 1 and 2, I would see that it goes up on either side. There is a y-intercept. Whoopsie. What's my y-intercept here? It's going to be 1, right? I don't know where these lines are coming from. Y-intercept of 1. Let's put it over there. And obviously something is happening at 1. Something unpleasant is happening at 1. The derivative is undefined. Yet, because I can see this as the cube root of x minus 1 squared, cube root is defined everywhere, this function is defined for all x values. So the function has no problem with any x values. It's the derivative that has a problem. And when I have a situation like that, for our level of functions, that's when I get the vertical tangent line, that there is a tangent line at 1. The only way the derivative cannot exist at the same time is if it's a vertical tangent line. Now I'm coming down and I'm going up. I'll give you a little, I guess, preview. You are not expected to know what this looks like at this stage, because we don't have all the steps, we're just doing one step. I make a sharp point there, vertical tangent line, vertical tangent line. The more I see this, the better it'll get. I have a function value, it's defined there. The derivative is undefined, has to be a vertical tangent line. Okay, but looking at this function, if I did step 1, identifying it as the fraction power of x type, I know from the start to watch out for vertical tangent lines. And when I have all the steps, all the pieces will hint at that shape. So the more I do it, the better it's going to get. Slow and steady. All right. Again, feel free to interrupt me if you have any questions. like always. Okay, let's do an example with an exponential component. Those are probably my favorites because when I take the derivative, they're not going to be super difficult. I'm sticking to the natural exponential function. But at the same time, they give me more interesting examples than just polynomial or rational function, while not being too extreme with vertical tangent lines and difficult things like that. So I would do steps 1 and 2 maybe, or maybe a test question could just be find the intervals where it's increasing, decreasing. And I just realized we never wrote down our sentences here. I got a little excited about the graph. I'm sorry. We should write our sentences. Let's at least see the table here. Okay, so I can say here y, whoops, not eraser mode. You should always write your sentences. Y is increasing on 1 to infinity. Do I include 1 or not? Do I put a square bracket or a round bracket? I always want to make these intervals as big as possible. Even though the derivative is not defined, there is a point there. The graph is defined there. Include it. It's not about the derivative. It's about the function itself. And then y is decreasing on negative infinity to 1. Include it. If I compare any 2 points and 1 happens to be one of those 2 points, it's going down. It's part of that interval. So always write these sentences. I just forgot. Okay. All right. So before I move on to this example, actually, I want to classify these points that keep coming up that are interesting. When I look at this first example, I checked where is the derivative 0, where is the derivative undefined. We got an x equal to 1 coming out of that. And what I get here is a point where things are changing. It's going downhill to uphill. There's a turning point. It's an interesting point in the graph. We're going to call that a critical point. It's really critical to the property of the graph, to the features of the graph, to the type of graph that I see. Critical point is going to be 1, 0, the point 1, 0. Or I can say critical point at x equal to 1. Okay. Now, I don't have my other examples with me, but we saw other points coming out of this check, derivative equals 0, derivative undefined, and we'll call them critical points. So let me just classify that. A critical point, I won't be too fancy with this definition, is going to be when my function, my derivative is equal to 0 or my derivative is undefined. Undefined. All right, so those two situations could give me a critical point. And I always check those two. And, capital and, I have to have a point. It's critical, it's important for my table out of these two checks. And it has to be a point, meaning my function is defined there. There has to be a point there. Now, if you think back to, let me just go quickly find that example that we did, the rational function one. We did this You can look back on your notes. We did that yesterday. We found the derivative to be 2 over x plus 1. Everything's squared there. So when we then did our derivative equal to 0, we found never. Our derivative undefined. Yes, that was when x was equal to -1. This, however, is not a critical point because the function is not defined at x equal to -1. The original function has a problem there as well. It was a vertical asymptote, right? Quickly graph this. We had a vertical asymptote at -1. Horizontal one doesn't actually matter right now. We had a fundamental problem at -1. It jumps over. There is no point at x equal to -1. So it can't be classified as a critical point. It has to be critical, but it has to be a point for me to call it a critical point. Okay, so let's keep that in mind as we look at this function, and then we will see what the critical points are, if there are any. Okay, so I'm doing step 3. Step 3. Derivative is what I need to find. Clearly the product rule. Derivative of the first times the second plus the first times the derivative of the second. Now I want to clean this up. I want to know, moving forward, what is the best version I can get? Well, I'm going to take an e to the x out, and I'll have an x plus 1 or a 1 plus x left. That's the best I can make it look. I have a positive exponent there, so it stays above the line. Then I want to check, where is the derivative 0? Where is the derivative undefined? Always those two things. No more, no less. So now I have the luxury that I don't have a fraction to worry about. So it's going to be when either one of these two equals 0, right? It's going to be when either e to the x equals 0 or when x plus 1 equals 0. So I have from the second one, I certainly have a -1 for x. When is e to the x equal to 0 is my question to you. When is e to the x equal to 0? If I have a product, then I have to check each one of those factors, right? And whenever any one of them equals 0, that's an x value that I need to list. And I need to make sure I have all the x values. If I miss one, my table is going to be messed up. Everything is going to be messed up. I need to not miss one. So I get -1 from the second, x plus 1, obviously. But the other one, e to the x equal to 0, is also one that I need to check. But I know what my e to the x graph looks like, and I know it's always above the x-axis. It's never going to touch. There are none. So -1 is the only point. But you need to know. So never is the answer for e to the x equal to 0, and therefore I only have the -1. Picture the graph, read it off. It's all there. And undefined, all of these things are defined. I'm not dividing by 0. It's all good. So that's a never. So the only point of interest in terms of increasing, decreasing behavior is x equal to -1. I'll call this my potential critical point because I've done half of the check. I've done the top part. I need to make sure it's actually defined there. So we can check at this stage, or I'd like to do it after actually, but it doesn't really matter. I've cleaned up my derivative. I have a potential critical point. I'll check the function later when I write my sentences. I've sort of got into the habit of doing everything at the end. I don't know why my line is so long, because only -1 is a point of interest here. So everything I list, e to the x, x plus 1, and they together give me the derivative. It has to be multiplication or division. I could not have taken the top, which had 2 terms. Okay, e to the x, again, I read it off my graph, it's always positive. X plus 1 is 0 when x is -1. It's in multiplication, going to make the derivative 0. X plus 1, check it, it's going to go negative to positive. So I have a positive and a negative, gives me a negative answer. Positive, positive gives me a positive answer. So my slope lines are going to go down, horizontal tangent, up. It's a nice little cup shape that I get there. I don't know what my lines were doing there. Oh, there was one cup there. Whee! There we go. All right. Well, let's write our sentences. F is increasing on -1 to infinity. Do I include -1? Yes, I do. Because I have a y value, plug it in. I can get a y value. Now, I don't really care right now what the y value is. The important thing is that I get it. So y value exists. This function is defined for all x, because why not? E to the x is defined everywhere. X, no division by anything. There's no problem at all. I can maybe write without. I just don't want a decimal number here. It's going to be negative e to the -1, right? Whatever -1 over e is. Who cares? It exists. That's the only thing that's important. And f is decreasing on -infinity to -1. Critical point? Yes. It's at x equal to -1 because it came out of my check of the derivative and there is an actual y value. There is a point. Critical point. But of course I have no idea what the graph looks like. Who knows? And I'm going to leave this a mystery, because I don't want us to think that we're expected to know. I have no idea what this graph looks like. I need all the pieces of the puzzle. Personally, I still need all the pieces of the puzzle, unless I've seen the exact one before. The fact that I've seen maybe x times e to the -x is a completely different function. I can't guess even what this looks like. Does it have asymptotes? I have to do step 2. I don't know. But that's not the point right now. So in the midterm as well, in a test, you might be asked to just do a single step. And you won't know what the graph is. And you're not going to be expected to graph it either. Just make sure that you can write these sentences at the end. Very important. If you don't write the sentence, I cannot give you all the marks. I need to see that interval. I need to see what you're including and everything. Okay. Any questions so far?